Hello everyone and welcome to another video. Today I want to talk about why structs are larger than they appear. Let's say we have a struct. It could be a class in any other language as well. I'm using C++ as an example. You can check it in Go, Java, whatever. Okay. Now what we have here is a char initial for the initial letter of that person, integer ID, so the user ID, short balance because anyone using our software would be broke, and a 1 byte integer for age because we don't need that much a limit for age. People usually don't live after 100 years. So let's say we have this profile data, and what is the total size? So 1 plus 4 plus 2 plus 1 actually adds up to 8 bytes. But if you try to print its size using size of, you would get 12 bytes. So why is that happening? And it will happen in other languages like Go as well. So it's not a C++ quirk, like everything is C++ quirk, right? So why is this happening? Well, the answer to this is that compiler is adding padding for better memory alignment. Now I know what does that even mean? Most people wouldn't have gotten it, and that's fine. So let's just understand what that means step by step. And to do that, first of all, we are going to need to understand how memory works. Okay, so let me give you a short introduction on how memory works. Okay, so when you want to say a plus b, right, when you write c is equals to a plus b, what do you think happens? You fetch a from RAM, then you fetch b from RAM, and then you add them and then you put them where c is in the RAM, right? No, of course that's not what happens. Access to RAM is very slow. Okay, so what exactly happens here is the data that A has is first of all put in a register, and same for B. Okay, so if you don't know what CPU registers are, they are like the main unit by which we access data. We fetch the data first of all into our registers and then we operate on them. So you must have heard of something like EAX, RAX, all those registers, right? So we fetch them. So A's data is fetched into some register, let's say EAX, and then B's data is fetched into some other register. Then they are added using a CPU instruction add, and then the result is put into the memory location of C. Okay, so data is first of all fetched into CPU registers. So they're like 16 or 32 registers, I'm not sure, but they're registers. Okay, so CPU registers, that's where we operate on memory. Okay, so how do we get data here? Do we fetch it from RAM? If this is RAM, do we fetch from here? No, because RAM is slow, like I said. What we do is we use faster memory called cache. Okay, so cache, the data is first of all checked in cache. If it is not in cache, we fetch it from RAM. Okay, and then we put it in the registers. And now let's say you allocated A and B pretty much together on the stack, right? So memory address of A is something, let's say 1000. Okay, so the memory address of A, I'm gonna represent memory address by these brackets. So memory address of A is 1000, and memory address of B, which is how many bytes away? 4 bytes away, right? So 1004, right? Now let's say there was nothing in cache for now. When you fetch A, right, you fetched A from RAM, you put it in cache and you put it here in EAX. Okay, so register 1. Now for register 2, you will again fetch from cache, although this memory was pretty close to B, pretty close to A, wasn't it? So it makes sense to not fetch like small amount of data that we need, 4 bytes or like 2 bytes, 1 byte, but fetch a constant amount of data, and then if the next accesses are close to it, then we will save this fetching from RAM to cache, which is slow. Okay, because cache access is fast, and that means we won't have a cache miss. So that's exactly what we do. If this is our cache, the cache is divided into blocks of 64 bytes in most architectures, and that is called a cache line. Okay, so data is fetched in units of cache line, in cache and in RAM as well. Okay, so cache is associated with RAM in some way, but the data is fetched in blocks of 64 bytes. That is the cache block size, which is also called cache line. Now, this way, when you fetch data of 64 bytes, you will get from 100 to 1064. Okay. Now there's something wrong with this, but we'll cover that later. Okay. So we fetch 64 bytes. It should be like this, right? And now this access, they all both will be very fast because everything is in cache. So that is how memory is actually working, and there's not just one cache. Okay, let me just remove all this garbage that I have created. Okay, I don't know how to use Excalibur properly yet. So yeah, so when let's say these are the registers, then they fetch from CPU, I mean cache, right? And then actually there are multiple cache levels. So there's L1, there's L2, there's L3, and then there's RAM. Some can also have L4, but it works pretty much the same. You access memory in units of cache line size. Okay, and so if you find it at L1, you take it, otherwise you check from L2 and like update that and then go there. Otherwise you go to L3, and L3 is actually shared among CPU cores, and then L4, or it could be RAM or whatever. Okay, so this is the general way how computers use memory, because RAM is not very fast. However, cache is very fast, but we cannot make too much of it because it's too expensive. So to use this in an efficient way, we do this. L1 has fastest access but smallest size, L2 slightly slower access but slightly bigger size, and so on. Okay, so that was how memory accesses work. Now let's talk about why this is relevant. So now we know that memory access happens in units of cache line, okay, which is about 64 bytes pretty much everywhere. So let's see what happens when you have allocated a variable A. Okay, so this is the cache and these are the cache lines. So now this data, and this is, let's say, L1 cache. Okay, so this data is also fetched in blocks of cache line. Okay, you can only access one cache line at a time. Now when you want to fetch A, let's say A is present here. Okay, it's 4 bytes, so it's obviously gonna be less than 64 bytes. Math. So you fetch this, so you read this cache line and get that data. Okay, fetch would be like a wrong word, I guess. So you read this cache line and get the data, right, and put it into the register or wherever, right? Now what if this data was not here but here, right? So this is 64 memory address, this is 0, this is 64, and then this is 128. Let's say the data started from 126 and ended at 130. So 126, 130. So this crosses a cache line border. So that means to read this memory, you'll have to first of all read this cache line, then read this cache line, and then combine the results on the rightmost half of the first and leftmost of the second to read 1 4 byte data. And that is also very slow. So what we want to do when we write programs is that we want our memory to be properly placed in one cache line so that memory accesses are fast. Okay, so and for that to happen, what we want is we want memory to be aligned. So I'm gonna introduce what the definition of alignment is, and then I'm gonna explain how that fits into data being present in only one cache line. Okay, so let's remove this and let's talk about what is the definition of memory alignment. So we say that a block of memory, okay, let's say this is 8 bytes. Okay, so we will say that this block of memory is aligned when it is placed at a memory address that is a multiple of its size. So its size is 8, so it is aligned if it is placed at 0, 8, 16, 32, okay, I'm kidding, 24, I know math, come on, that was not an honest mistake. So if it is placed at these locations, then we say that the memory is aligned, or the memory has an alignment of 8 bytes because it appears at memory addresses that are multiple of 8. Okay, so this memory has alignment of 8 bytes, and because that is its size, it is aligned. Okay, so now let's say this was our cache itself. Okay, now notice that, okay, let me take a better example which will be easier to draw and everything. I'm sorry, I'm so bad at this. Okay, so let's say we are checking for 16 bytes. Okay, so it will be aligned if it is present at 0, 16, 32, 48, 64, whatever, then 128, whatever, right? So if it is here, it has alignment of 16. If it is here or here, so yeah, you get the point. Now let's change this color and draw the cache line boundaries. Now cache lines are 64 bytes, right? So these are cache lines. Now notice that cache lines themselves are aligned, and that means they have an alignment of 64 bytes. Okay, so cache lines themselves are aligned. So if we allocate the 16 bytes with an alignment of 16, we are guaranteed for it to be present in only one cache line. Why? Because see, this is in the same cache line, this is also, and this is also, and this happens because 16 is a factor of 64. So this alignment condition, which means that the memory is at an address that is multiple of its size, what this ensures is that this memory appears in one cache line only. But there's two more conditions, obviously, that this memory has to be less than equals to the cache line size, which is C, right? And this also has to be a factor, right, of cache line size. So 64 should be divided by 16. And now let's talk about what is the condition for alignment of primitive data types. Now we want them to be aligned, okay, but let's see if that actually works, right? You will see, okay, let's go back to color gray and let's remove this. Now what you will notice is that char is 1 byte, short is 2 bytes, integer is 4 bytes, float is 4 bytes, double is 8 bytes, long is 8 bytes. All these are factors of 64, right? So that means if they are aligned, then they will also lie in the same cache line, and that is because they all divide 64, right? They all divide 64. So okay, and this is exactly what the condition for alignment of primitive types is. We want them to be at a memory address that is a multiple of their size, because their size is a factor of cache line size, and cache line is aligned. So when something that has a bigger alignment is aligned, then something that has a smaller alignment which divides it, will also be aligned properly inside of that. So yeah, I just overcomplicated it, but just wanted to put it clearly once more. Okay, so now I know what you might be thinking. Hey man, I actually learned that long double is 64 bytes. 10 bytes. If you don't know, so I did explain floats and all that in my previous video. You can check that out there. But so floats have some precision bits and some exponent bits. Now our normal double does not have enough precision to store everything that is in a 64-bit integer. Okay, so we created another data type long double that has enough precision along with mantissa to store all the integers that a 64-bit long can store. So that is why it has 10 bytes. Okay, if you don't know what mantissa and all that is, mantissa is just precision bits, but you can check my video for better clarity. Now this is 10 bits and 10 bytes, and if we have alignment of 10, that would not ensure that data is in one cache line, because what if we start from 60 and go till 70, right? That would come in multiple cache lines. Well, here is the solution to it. Let's go to Godbolt and print out the size of a long double on x86 architecture, 64 bits, sorry. And when we run, we get 16 bits. I mean 16 bytes. What am I talking? Yeah, 16 bytes. Right. So although the data type actually has just data enough for 10 bytes, compiler or like the implementation, whatever, is padding it to be 16 bytes because we want it to be memory friendly. Now, why not just have 16 bytes amount of data? Because then float processing unit will be slow. So that was that. Okay. So yeah, long double also works because it is not 10 bytes. It is either 12 bytes or 16 bytes or 8 bytes. Okay. Because in some compilers, it does not have enough precision of 64-bit integers. No, they just have normal of double. Okay. Normal that double has. Okay. So with that said, primitive types. So we have talked about the condition of primitive types to have an alignment and why we need that alignment, because that alignment will make sure that it is present in only one cache line. Now, what if they are in a struct, right? Now, data types in a struct are stored contiguously, right? So let me just, bro. Okay, thank you. So now, don't want to show others. Okay, so let's take this struct. I want to take a screenshot, man. Come on. Okay, so let's take this struct. Go over here. Okay, make it a little bit bigger. So okay, so this struct, let's consider what is the now. Do we want this entire struct to be aligned? What does that even mean, right? Because when we access some data in it, what we are really accessing is some member, right? Some element inside of it. So what we really want is we want all of these member variables to be aligned. So let's have a look. Let's say it starts from 0. Now char initial will take 1 byte, right? So initial comes here, memory is here. Now id, see, id is a integer that is 4 byte size, right? For it to be aligned, it has to be a multiple of 4. So we cannot start from 1. So what compiler does is it adds some padding. And that is 3 bytes. So this is some padding, and now memory address starts from 4 and id gets over here. Now it takes 4 bytes. Memory address is here 8. Now balance is a short requiring 2 bytes. So we want it to be at a memory address that is multiple of 2, and yeah, it is a multiple of 2. And I just want to point out one more thing, that because the previous memory was aligned by 4 bytes, that means the next memory we will put after it will be aligned by 1 byte, 2 byte and 4 byte, right? Because they are factors of it. So yeah, this will come in to later. Okay, so yeah, 10, and then we add age. So age 11. Okay, so that means the actual size should be 11 bytes, but we actually got 12 bytes. Why? Right? That is a good question. And the answer to it is, well, great. Actually, we just need 11 bytes if we are allocating one struct. Okay. If we are allocating one struct, all we need is 11 bytes. But what if we are allocating an array of structs, right? So let's say this is the array of structs, and the first is, let's say, starting from 0, but the next will start from 11. And notice that from when we started from 0, we knew that we can start from whatever, right? We can have ID as the beginning, and it wouldn't matter because everything is aligned, right, at 0. But at 11, if ID, if it was something like ID is first and then character initial, then that would mean that putting this element here would not be the same memory layout, right? The alignment would change. So let me actually think of a better example here. So 4, 5. Well, actually, let's go with this, right? I mean, there's no guarantee, right? 11 is a factor. I mean, 11 is not a multiple of 4 or 2, right? So if actually, I want to take a better example. I'm sorry. So 4, 5, 6, 7, 8, 9. Yeah, this looks like a better example. Okay, so let's quickly catch up to what we had written here. Let me just remove all of this. Okay, so let's paste. So let's write down its memory layout again. So ID int is naturally aligned, right? Then character is also aligned, initial, right? But balance is not aligned, so we add 1 byte of padding, right? And now balance is aligned. And then we have an age, so then age, right? Now this is even smaller with 9 bytes. But notice, what if we allocate an array of this, right? So the first 9 bytes are good, right? Every element in that is aligned properly. But now, if we have the same memory layout, then notice that this integer ID would not be aligned because it is starting at 9, right? It is starting at 9, so it won't be aligned, right? This ID won't be aligned. And so the alignment messes up. So how can we make sure that even if we allocate a struct, we get proper alignment? The way compiler ensures that is that we want the overall alignment of the struct. That is so overall alignment meaning the start of the memory address of this, right? And yeah, so we want that to be also a multiple of whatever is the size of the largest element. So I'll explain. So what we want is the alignment of the struct to be equal to the alignment of the largest element in that struct. So in this struct, the largest element is integer ID, right? That is 4 bytes. So what compiler does is, it pads in the end 3 bytes. Okay, no, not a line. Okay, yeah. So it pads in the end 3 bytes to make it 12 bytes. So that its size is a multiple of the alignment we want. Why? Because then the next element in the struct will start from a multiple of 4 bytes, right? And yeah, then it will have a proper alignment. But how does that make sure that this memory layout will have every element sharing proper alignment, right? Because that is why we are doing this. That is why we are adding this padding. The answer to that is that, remember what I said, cache line has an alignment of 64. Now a data type, let's say id int, has alignment of 4. Now it will remain in only one block of a cache line because 4 is a factor of 64, and you can see this by drawing it, right? We did it for 16, right? 16, 32, 48, 64, then it overlaps with the cache line, then blah blah blah, and then 128, blah blah blah, blah blah blah, right? So due to this, notice again that every element is smaller than the, okay, how do I remove this? Yeah, so every element is smaller than 4 bytes, right? Because like I said, we are taking the biggest element and we are making the overall alignment of the struct to be equal to the alignment of this, that is 4 bytes. And to do that, we have to add some padding so that the next element we allocate starts at a multiple of 4. And that is why 1 byte of padding here and 3 bytes of padding here makes the total size of profile 12 bytes. So yeah, so for primitive data types, for alignment, for them to be aligned, they have to be a multiple of this size, right? And that is actually ensured by our compiler and whatever the OS APIs are, that the memory allocation is aligned. And for struct as well, this alignment condition is maintained by adding some padding if required, and yeah, making sure that the overall alignment is same as the alignment of the biggest element. So yeah, that is the condition. Now I'm gonna give this to you as a homework. Now what do you think is the alignment condition for something that has a size, a struct, you know, that has a size bigger than 64 bytes, because it won't fit in a cache line? Actually, let me give you the answer, but you can try, right? See, we don't access the whole profile at once, right? We don't put everything into registers at once. We deal with member variables, right? We deal with primitive data type. So to do that, what we have to do is, we just want to make sure that these elements come into one cache line at a time and not the whole struct. And that is why this alignment condition works, because 12 is not a factor of 64, right? So this is something I wanted to mention, but I also wanted you guys to think about it. So anyhow, with that said, let's talk about, now this is obviously not good, right? Because this is taking 50% more memory than it requires. So what can we do? Well, the answer is very simple. Remember, the struct overall will be aligned by 4 bytes, right? That the allocation will take care of. We can change the ordering to maybe like minimize this padding, can we? Let's think. Now, it is the starting memory is aligned by 4 bytes, right? That is the largest member element size. So that means, what if we first of all put all the members that are 4 bytes? So if we put them, we will still have alignment of 4. Then we can put all the member variables with 2 bytes. And then we will have an alignment of 2, right? Because 4 is a multiple of 2, so we can assume that it was alignment of 2 as well, right? And then we can put 1. So if we declare members in decreasing order of their size, so like this, then the size would be 8 bytes. But because the overall alignment of the struct has to be maintained, right? This would also have 8 bytes, because compiler will add some padding. And if you're wondering how padding is, it is just like this, like padding 0, 2 bytes of padding, right? Because we want this to be its size to be a multiple of 4, so that when other members of, so that when a array allocation is done, then the other members are also aligned. So yeah, so how can we get rid of this? Well, there are 2 ways to do that. One is to tell the compiler that you kind of don't care about the alignment, just make it packed, okay? So this way This way compiler won't add the padding, and you will have 6 bytes. But with this, the alignment would not be satisfied. Okay, so if you know what you're doing, you can do it, right? So if, and the other way is to maintain alignment, and what you can do is profile ID. Now there is just one element, but there could be more elements. Now profile other. So you create 2 structs, right? And then you, if you want to allocate an array, you allocate 2 arrays. So yeah, that's another thing. Now this actually does have some issues with it, and the main issue is that if you allocate 2 arrays, right? So let's have a look at what happens when you allocate 1 array and when you allocate 2 array. So when you allocate 1 array of 8 bytes, right, you have data like this. And so if you have accessed the ID, then the balance is also in the cache, right? Because they are very close to each other. So you can access that and all will be good, right? However, if you have allocated 2 arrays, one with just ID and one with just balance, so ideally it would be something like this, right? And then balance is here. Then if you access ID here and access balance here, there would be a cache. There could be a cache miss. Okay, so yeah, this is more cache friendly and this is less cache friendly, but this is more memory efficient, this is less memory efficient. So it's all trade-off. Okay, and by the way, this is array of struct, this is struct of arrays, right? Because there are multiple arrays. One is array of ID and one is array of balance. So yeah, this was this video, right? We learned about why structs are larger than they appear, right? And how can you, and why is that so? Because compiler adds padding. Why they add padding? For memory alignment, for better memory access speed, and how you can mitigate that by having a decreasing sequence of member variable sizes, right? And we also talked about the trade-off between something like this and let's say something like this, right? Separating structs out and then making array of both of them, right? So this is, that previous one was if you make an array, then previous one would be array of structs, this is struct of arrays. So yeah, I just mean this, right? So profile these and profile other. So yeah, so notice that it's kind of a struct of multiple arrays, but if we have everything in one struct, then what we form is just one struct. So array of structs, right? So profiles. So yeah, that we also talked about their trade-offs. So yeah, hope you learned something new in this video regarding memory and memory accesses, structs, arrays, whatever. If you did, leave a like, subscribe, and I'll see you next time.